Hello guys, in the last video we managed to get the Advent of Code 2024 day 7 completed. So in this video let's jump to the day 8. And without further ado, let's connect the runtime and check what is waiting for us. If we get the day 8 open, and we could connect this already. So day 8, resonant collinearity. You find yourself on the roof of Top Secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is turned to specific frequency indicated by a single lowercase letter, uppercase letters, or digits. You create a map, your puzzle input, of these antennas, for example. So these are the frequencies, okay? The signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So for these two antennas with frequency A, they create two antinodes marked with adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map, so instead it adds only 2. Antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes but has lowercase a frequency antinode as its location. Antennas with different frequencies don't create antinodes. Capital A and lowercase a count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes but has a lowercase a frequency antinode at its location. The first example has antennas with two different frequencies. So the antinodes they create look like this, plus an antinode overlapping the topmost A, capital A frequency antenna. So these antinodes are because of these two capital A's. This antinode is because of this, and this antinode is because of these two. Okay, I can see, okay. Because the topmost A, capital A frequency antenna overlaps with a 0 frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal, how many unique locations within the bounds of the map contain an antinode. Okay, let's get our puzzle input. Okay, luckily it's relatively small. So if we start by in our map and then let's split it as usual from the line change, and then so what we need to do is we need to locate locations, or first of all we need to get all of the different frequencies, I think, and then their locations, and then per frequency we can then start to calculate the positions of these antinodes. So what we could do, let's actually add not a code block but text block that says day 8 part 1. Yes. So if we start by that, so if we have frequencies, or it would be a list actually. And then if we would create this data class for every frequency, frequency, yeah, and it would have the basically the character that it represents the frequency. So is it ID, which is string, and then locations, which would be a list of tuples that will have an integer values, so x and y. And for this, we could have separate data class. Let's actually create data class for that as well. So basically it's a location that would have x as an int and y as an int as well. So then we can have just list of locations. I think this is a good idea. And I think we can run, or maybe let's not run that. Let's run just these so we can have those available. And then we can start by locations. So the list of or frequencies actually might be. And let's keep it like this so we can kind of access it more quicker. So if you have a key as a frequency ID and then the frequency itself as an value. So if we look through the rows for we need to enumerate the rows for so rows are y, so for y, and then row in enumerate, and then for x and col or char in enumerate row. And then we need to check that, since we know that dots are just empty spots. So if char is, or we can even check like this. So if it's a dot, then we will just continue. And if it's something else, then we first check that do we have it listed in the frequencies dictionary already. So we can do so that we will do get so frequencies get char. So this should return the existing frequency if we have it in the dictionary. And then we can check if frequency is none, so it's not existing. So this by default sets it default value. We can declare it here as well if we want. So if it's none, then we can do so that we'll create a new frequency, and the ID for that is the character, and then the locations for now will be just list where we can add the current location where we found the current item, so x and y. And we can of course do like this so it kind of stays more readable, and then x is x and y is y. And now, so in space we know that we have the frequency available. If it was created, we can actually do it so that we will just and we need to actually set it here to be the one for this frequency. And then we can continue. So basically, if it didn't exist, we created it, added the first location in, then added it to the frequencies dictionary, and then continued to the another next value. But then if we had it already from here, so we have some locations in it already, what we need to do is that we will set frequency dot append, and we will create a new location, basically same way as we have it here. And then after the appending, we need to update the frequency in the frequencies dictionary. And actually we can see that we have some duplicated code already, so technically we could even do so that we will not continue or remove the continue and update. Then initially we just set the locations to be empty list. And this we will continue until we have exhausted every character. So we can actually run it already. And now if we check what we have in the frequencies dictionary, we should have a quite nice list of items. So in total we have, how many frequencies we have? I think dictionary set keys function, 60 frequencies, nice. So what we next need to do is we need to start figuring out the locations of the antinodes. Let's see. So I'm wondering how did it happen, behave. So antennas with different concrete antinode count as different frequencies. However, antinodes can occur at locations that contain antennas. So doesn't matter if there is an different signal frequency set into the place of antinode. Okay, so there should be 14 in this picture. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then the most A overlaps with 0. So I guess which 0 it is overlapping, because the topmost A frequency antenna overlaps with O frequency. So basically I guess it's yes, so it's this 0. Okay, yes, we have 60 frequencies, so we can start to figure out how we can calculate the antinodes. So basically def calculate antinodes. This will take the frequency locations in, and then I think we need to, for location in frequency location, I guess kind of this brute force way again in this task. So for every location we need to check the every other location that we have, that are they aligned so that we will have an antinode in the current map area. So if this is L1 and then we have L2 in frequency locations, and then if L1 and L2 are same, we will continue, because we need at least two different locations. And was it so that we can between every, so it's always 2. The signal only applies its nefarious effect specific antinodes based on the resonant frequencies of antennas. In particular, an antinode occurs at any point that is perfectly in line with 2 antennas. Okay, yes, correct. And so if L1, L2 are different, we can calculate the diff. And this is kind of reminding me of previous days puzzle. We actually tried to kind of figure out the similar behavior or calculate kind of the positions. So let's get x1 which is L1 like this, and then Y1 which is like this, and then same thing for the L2. So now we know where these frequencies are located. So now we need to figure out new x for the difference between these. So x difference is basically this x1 x2 minus x2, and then we can calculate the same y. And now how we can use this info, what is the difference between these two locations. So get the so we need to approximate or calculate where is the kind of location before and after. So if we have these two a's here, we need to calculate this hashtag and then this one. And actually, should we then, yes, so to calculate these, we need to actually store them as well. So we should have on the node location, which is an array, and then in the end of this function we should return on the node locations. And now when we have x1 y1, so on the node 1 is located at x1 minus x diff, and then y1 minus y diff, and then on the node 2, we can name it like this, or is located in otherwise same, but now like that. I kind of feel that this might be now off. Let's confirm. So if we think about this picture, so we have let's actually copy a bit more, copy these as well, and then we create the L1, which is this one. So it's y1 x, and then L2, which is located in, oh sorry, it's not that, it's this location we need to check. So it's x3 x4 and y3, and then this location is x4 5 and y5, like this. And then if we print on the node 1 and 2, we should get two values that are not different. So is it like, let's check the diffs, x diff, y diff. Oh, typo. So they are minus, so actually this is white. I had some thinking error there as well. So now we actually know that this needs to be a plus. So now it should be correct. So 3 and 1 is this, and then x6 1 2 3 4 5 6, and then y7 1 2 3 4 5 6 7. So it's correct. So we can say that this is now how it should be, and we can delete this like this, and then for just confirming that we are safe, so everything is working, let's use this kind of smaller example map that's given to us. Example map like this, and then we can say like that. So we don't have just 3 frequencies. We don't have 3, but we can just skip those characters. So we have 2. Why we have 2? Which are the frequencies now? So now we should have just 1. Yes, correct. And all the locations set as they should be. Correct. And then if we run this and try to use it, so we have for let's see, so this one's the locations list. So actually we should be able to do just on the node calculate on the nodes, and then if we give it this frequencies get a like this, we should frequency of it is not iterable. Yes, correct. Locations in other hand should be. And since we did it like that, make this way cleaner. So this is just L1x, L2x, oh sorry, I guess L2x, and same here, and then L2y. Yes. Now it should work, and if we print the on the nodes, what we will get? Empty list. Yes, most likely, or it would work better if we would also update the list. So we need to, or we could do maybe this way. It's a bit. So now if we run it and then run this, we can see that there is many, but we have these duplicates. So if we would make this a set and then just add these to the set, add on the node 1 and then on the node 2, I think we should get a bit better list. Yes. So this does not solve the issue completely, but we have also one thing that we are not taking in account here, which is that many of these, I think, are over the limits of the map. So if we start limiting those map size, actually before that we could check that is our map kind of looking how. So what is the size of the map? So it's 50 by 50. So we know that we can live with map size or one number. And how to make this work? So basically we need to check that it's on the node. We could actually create these as some locations as well. I think it should work nevertheless. For this it's example map and length of that. And yes, maybe we just keep them like this, and then we need to just check that if on the node A or on the node 1 is bigger than is, I think, did we have a way in Python? Let's check to compare if A is 5 can we write like this? I think we might be able. Good. So we can check that if this is 0 or bigger and then smaller than map size, and same thing for the second value, and then same check for the on the node 2, And yes. So if we now run this and then run that, we are limited to 4 items. And those items are located in, so we had 4, so numbers are matching. So the first one is x3y1, correct. Then the next one is x6y7. Let's go check. 1, 2, 3, 4, 5, 6. Okay, and then y's 1, 2, 3, 4, 5, 6, 7. Correct. And then O and 2 found. Then x2, y6. Yes, here. So it seems that this is working. So now we can proceed with the real deal. So instead of example map, we will use the input. We can get quite many frequencies, and then what we need to do, calculate the total unique locations that contain an antinode within the bounds of the map. Total unique location. So we need to also store these antinodes in a set, and then we should be able to do just this. So access the locations from the given frequency, and then we should have all antinodes or antinode unique antinode locations. And then if it is just set, and then we can do add. Now I wonder, does this allow adding like this? Actually, I think we should be able to, or can we? Let's try like this. How does it behave? So if we run it, it will error out. So can we do it then by just using the plus operands? Or do I need to Google a bit? I think I need to Google. Then update. So we can just do update and then antinode. This should do the trick. And we can actually remove this one. Let's see what we have in the unique antinodes location set. We have quite many items. Looks good. So the question was, how many unique locations within the bounds of the map contain an antinode? So if we just check this one, it says 367. If we submit that one, and that was a correct answer. So this was, I think it felt at least a bit simpler than the previous one. Let's see what the part 2 brings to us. But I think it's good to pause here so that the video won't get too long. So thank you for watching and see you next time. See ya!